Welcome back. Today we are starting our lesson number 5, and in our fourth lesson we learnt about the greatest common divisor and many of its properties. So today we are going to look at what's called Diophantine equations. And what is that? It's a linear equation with integer coefficients and integer solutions. So we want to try to solve an equation that has integer coefficients, and the only solutions we are interested in are integer solutions. So the first type, the easy one, is one variable, ax equals b type. Now you can see, if I have an example here, 2x equals 7 has no integer solution. The only solution is 3.5, and that's not an integer. So there is no integer solutions to this equation. Whereas this has an integer solution. And we can therefore derive the criteria for solutions to exist. In this class we are only looking at integer solutions. So if there are no integer solutions, I'm going to say no solutions. If has integer solutions, if A divides B, then we have integer solutions. So that's the easy one. Let's look at a bit more complex equation when we have two variables. So I want to look at an equation that looks like ax plus by equals c. And now we have a theorem here, a proposition that let D be the greatest common divisor of A and B. Then ax plus by equals c has integer solution if and only if D divides c. So that means this equation here has no integer solutions, because the greatest common divisor of 33 and 18 is 3, and 3 does not divide 14. So therefore this equation here has no solutions, no integer solutions. Whereas if we change it and look at this equation, 33x plus 18y equals 15, it will have integer solutions. And because now the greatest common divisor 3 will divide 15, an example, we can have this as one of the possible solutions. And when x is 1, y is negative 1, solve the equation. Now because this has two variables, there are an infinity of solutions. This is just one of them, because we have 1 degree of freedom. We have two variables and only one equation. That means one variable will be free and it can take any value. So that if there is one solution, there will be an infinity of solutions. Solving Diophantine equations is very easy. So first we want to find one solution, and for that we can use the extended Euler algorithm. Remember, we had a table to write the greatest common divisor as a linear combination of A and B. We did a table in the last lesson. So since our greatest common divisor is 3, I can use the extended Euler algorithm and find the linear combination that works for 3. So you will see that if you do it, negative 133 plus 218 is equal to 3. Now what we want is to solve the equation. Since greatest common divisor divides C as a criteria for existence of solutions, we multiply this whole equation by 5 to get to our 15. So then negative 5, 33 plus 10, 18 is 15. Therefore straight away by inspection we have another solution. X equals negative 5, y equals 10. And that's our first solution. I mean, we already had another solution as well, but so we can now develop it to find all the solutions. So we can use this theorem to find all the solutions. So let ax plus by plus c be an equation with integer coefficients. If x0, y0 is an integer solution, then all the solutions are given by this formula. So then x is equal to x0 plus b over dn, y equals y0 minus a over dn. So with this formula we can write all the solutions, and for example it's given by, I'm using this solution negative 5, 10 as my first solution, and so this gives me all the solutions for every integer n. So you will see there are an infinity of solutions as n cycles through all the integers negative, 0 and positive. You get an infinity of solutions. Graph this and see what it looks like. 33x plus 18y equals 15 is a straight line graph, and another way to look at it is the graphical method, and you want to see this line, where does it have integer solution. So you can see that if you graph this line, it will go through an integer at 1, negative 1, and the next time it goes through an integer is negative 5, 10. So the other points on this graph are also solutions, but they are not integer solutions. Okay, we are only interested in the integer solutions. There are an infinity of integer solutions on this graph, and they do go through integer values, and those become our integer solutions. This brings us to our next topic, congruency. And again, a very simple idea. Let m be a fixed integer, so it's an integer that we know, a positive integer, that's important. Then two integers a and b are said to be related congruent modulo m if m divides the difference between a and b. So if a minus b gets divided by m, then we say that a and b are related, through congruent modulo m. And we write this relationship between a and b in this form. So a is congruent modulo b mod m. So we read it, a congruent modulo b mod m. So that means a and b are related. There is a connection between these two integers a and b, and the connection is through this m, the integer m, and the connection is that a minus b can be divided by m, is a multiple of m. So for example, if I have 7 and 12, I can get a connection between 7 and 12 through modulo 5, because 5 will divide 7 minus 12. So a minus b gets divided by 5. But of course, if I change my modulo and look at a different modulo, say modulo 4, then 7 and 12 are not connected, they are not related, they are not congruent modulo 4, because 7 minus 12 does not get divided by 4. Okay, so the modulo m plays the key role to see whether two integers are connected through that. And here are some more examples you can see. So suppose I have two other integers, 36 and 24. They are connected through modulo 2, because if I subtract 36 minus 24 gets divided by 2. So 36 and 24 are congruent modulo 2. And it's also congruent modulo 4, that's another m. So we need to have one m, but you can see that between two numbers there can be many connections, okay, all through this congruent modulo m.